Yeah, I want to talk about data-driven fluid modeling in SU2. In particular, for all the applications I made is regarding physics and core methods for the application of modeling non-ideal fluid flows in SU2. I think all of us are well aware of the ideal gas law we've learned since high school. That's used in most kind of flow simulations in SU2, which is very applicable to atmospheric flow simulations, combustion flows, many examples. However, there are conditions where this ideal gas law is inaccurate. The case, for example, when you're modeling flows of complex organic fluids, flows at high pressure or close to the phase line, um, then these type of flows are relevant for things like novel energy applications or extreme conditions. Now, SU2 has several fluid models available for modeling these types of flows. For example, Bang Robinson, the coolprop Webber, which uses the Helmholtz equation of state, and there is the data-driven fluid model, which I'm going to talk about more today, and some of the new things that I've been working on. So first, I'm going to give a very short primer on the data-driven fluid model in SU2, how it works, some of the new things regarding physics-informed modeling. I applied this to modeling flow through organic Rankine cycle turbine. And then I'm going to give you some hints on what I'm working on next. Now, a data-driven fluid model in basic works as follows. You take the flow transported quantities, you feed them to a data set, and you get your state variables, which you use to close the system of equations. In SU2, we are using an entropic equation of state, which ensures consistency between the state variables. Now, this works as follows. You take the fluid entropy and its partial derivatives with respect to density and internal energy, and you feed those to the entropic equation of state to get your state variables. Now, you obtain these partial derivatives through interpolation of a data set. So you take your density and internal energy, feed them to a multi-layer perceptron or a lookup table, and you get your derivatives. Now, this works relatively well, although training for these type of variables is quite difficult, especially obtaining the second order derivatives can be quite challenging to interpolate properly. And also, it's sometimes impossible to access these kind of data. So, with simplification of this model is to, instead of interpolating these quantities, you just compute the Jacobian annihilation of the MLP at runtime. So basically, you have a multi-layer perceptron with two inputs and one output. You analytically compute the Jacobian annihilation to obtain the second order derivatives, compute your state variables, and close your system of equations. So I want to pause on this that I find very interesting is that you have a multi-layer perceptron with two inputs and one output, and with that you can compute the entire vector of state variables. Now, of course, you need to train this MLP in a way that it works properly in SU2. Now, for this, you need training data, which can come from basically any source. Those being density, internal energy, and a set of primary or secondary flow variables. For these, you set up a training loop, a TensorFlow, for example, to train the network weights to match your state variables. Now, over the original method, this has a couple of benefits. First, namely, in that because you're analytically deriving the Hessian and Jacobian, this method has improved consistency. In fact, consistency is implied. Also, because you're training on state variables rather than derivatives, it's much easier to obtain the training data. You could even take experimental data to train this method. Now, why would I go through all this trouble if SU2 has perfectly working coolprop fluid model wrapper? Now, the first benefit of using the data-driven fluid model is that this is compatible with Evert. Also, depending on the network architecture that you're using, it can be much more computationally efficient. Now, I think we have all been in this situation where you read a paper that has a really nice workflow or method outlined, but then getting access to this method is a matter of sending an email and maybe receiving a reply a year later. So I want to make sure this doesn't happen by making a contribution to the SU2 community by setting up a robust and publicly available workflow for this setting up these data-driven simulations in SU2. Currently, this goes under the name of SU2 Data Miner, and it can be found in my on my GitHub page. This workflow allows you to generate and process fluid data, write it to a manifold in the form of a lookup table or multi-layer perceptron, and then convert it to SU2 compatible files, which can directly be loaded in SU2 for fluid flow simulations. And it offers hyperparameter optimization as well. Currently, this method has been developed for the application of non-ideal CFD and failure-generated manifold simulations in SU2, which we're also going to hear about later today. As I said, it's available on GitHub, and I'm in the process currently of setting up a set of tutorials so new users can get to use it easily. All right, so now let's talk about application. For this, I modeled the flow through an organic Rankine cycle turbine stator, which you can see the geometry on the right, and it's very reminiscent of the type of experiments we run at TU Delft at our facility. I'm not even going to try to pronounce the fluid name, just going to call it MM, which is an organic molecule. Now, for this type of simulation, modeling of non-allele fluid flow effects is highly relevant. As you can see here, the flow conditions go from near the critical point to almost ideal gas conditions. And here on screen, you can see the training data that they used for setting up the data-driven fluid model. The training data that they use obtained from RevProp and used temperature, pressure, and speed of sound as training data with a very simple neural network as the MLP that they used. Only 40 neurons with a single hidden layer. And yeah, a pretty typical turbomachinery, second-order turbomachinery setup for running the SU2 simulation. And here I ran two simulations, one with CoolProp and one with the data-driven fluid model to compare. So the first thing that I did was to verify whether the fluid model was behaving properly. And for this, I interpolated the thermodynamic state from streamlined data uptakes from CoolProp. So here on screen, you can see the streamline, maybe a bit hard to see in this slide. And on the right, you can see the interpolated state variables from CoolProp in blue and from the neural network model in red. You can see that they match quite well with an overall average prediction error less than 0.25%. So then simulation results. Now, again, yeah, maybe a bit hard to see, but quantitatively, shock structures seem to be captured pretty well between the two models. In terms of evaluation time, the gains were actually quite unexpected in how efficient this model was, because despite having to differentiate the MLP twice and having to run Newton solver iterations at environment conditions, the data-driven fluid model was almost 3 times as fast as the CoolProp fluid model at runtime. Now let's look a bit more detail, because it's not all sunshine and roses. There are still some differences here. If you look at the shock structures, especially downstream, there are some differences. So here on the right, you can see the Mach number on the outlet, and you can see that, yeah, there are still some small but not insignificant differences between the two results. And especially in terms of temperature and total pressure, the differences become notable, although the trends seem to be captured quite well. Now, one of the reasons why this happens is that there's one issue that I have no idea what the source is for yet, and that's a non-physical rise in temperature along the supersonic boundary layer in the ideal gas region. As you can see on the right and the CoolProp on the left and neural network on the right, there is a non-physical rise of temperature. Basically, the static energy rises until the bounds of the training data, and then it's get there and it doesn't get out of there. Um, I'm currently investigating where this comes from, and one potential issue might be the fact that the network has some significant errors in the ideal gas region. As you can see here, the pressure prediction error rises to almost 5% at the trailing edge, um, as well as some of the secondary variables. So, yeah, just to summarize my talk for today, I developed an open source workflow for setting up data-driven simulations in SU2 called SU2 Data Miner. This allows the data-driven fluid model in SU2 to use a physics-informed documentation, which makes the method more robust and easier to train. When applying this to a flow simulation using the Orchid Cascade, initially there was an accurate prediction of its primary flow variables and a significant gain in computational efficiency, while also allowing for agility and cleaning. However, there are still some non-physical things to work out, especially in the ideal gas region. So that's what I'm going to work on. Next is to improve the model predictions in this region, possibly through some clever pre-processing of the training data. I'm going to extend the SU2 data miner workflow so that it's going to be accessible to the whole community, and one day bring it under the umbrella of the SU2 organization. And yeah, also do some fun stuff like experiment with different fluids and its mixtures for some wacky simulations. So thank you all for your attention.
I have a few questions. One, is it possible for you to do these in validation there, as you mentioned, you could use experimental results as well as tables and equations here. Is that providers?
Sorry, so your question is whether you can use like
Global data sources.
no, so far I've only used one. But in principle, like as long as you have a distribution of density, energy, and state variables, it can be only temperature, only pressure, only speed of sound, or secondary variables, it is theoretically possible to train this. But the SU2 data miner in its current form has a workflow for also generating the fluid data, which is currently only through CoolPro.
Yeah, because the department decides that you may gain that computational efficiency, and you also should sign that should on slide 15 you have the box. So I think that guys what conditions do we see works computational performance and also to even make a consideration to the memory. And I would call it failure like you.
Yeah. So the computational time scales quadratically with the network size of the network architecture, because you need to do several matrix multiplications throughout the network to compute the Jacobian and Hessian. So keeping the network small is of importance when limiting computational time. Now, in terms of memory, it's really negligible because you're only loading like 2 matrices of floats to store the network. So that's really not an issue. And also with some joint computations that I ran, the memory overhead of the trace is actually not that big compared to like what you would expect for like Penn Robinson.
Okay. So here, I think I'm up first. You guys.
I just wanted to follow up on very quickly on the question of Josh. I do not understand what would be the use of training data on both an equation of state, highly optimized as the one you mentioned, and more experimental data. Because normally the equation of state is optimized on those experimental data. So what would be the advantage?
So the I don't think I really understood the question.
So Josh mentioned the possibility of training or uses as sources for training both numbers generated by the equation of state model And
Well,
experimental data.
The numbers are not generated by the equation of state model. The training data can come from anywhere. It can come from like Helmholtz equation of state, can come from experimental data, but then the equation of state used in SU2 is optimized to match these data. So you do not use the same equation of state to both generate and model the data. The source of the data can come from anywhere, but then you use the entropic data to try and
What you call the equation of state in SU2 is the entropic equation of state.
it's it's a model.
My question is, why would you train this equation of state on another equation of state, Helmholtz space, plus experimental data? Because I cannot picture a situation where, I mean, Helmholtz equations of state are highly optimized on all best experimental data there are.
Mm-hmm.
So I don't understand why adding the same data can be split.
I think the statement of Evert, I mean, to into your pen, was simply saying that the model has been set up in such a way that you can use any data from any source, irrespective from whether you use a Helmholtz-based equation of state, which is either optimized with experimental data, or you use just experimental data on the field on which you don't have Helmholtz equation of state. Then you either or you can ask whether they can do that for you, or you could use the method of Evert and just exploit the data.
No.
Okay, we only have 1 minute. This is your hand was up. Why don't you ask a question while we start the